Welcome back, ladies and gentlemen, and now we'll begin the technology session 2, Hydrogen Readiness. First of all, I would like to introduce two moderators for this session. First of all, Professor David Sandalo, ICEF Steering Committee, Inaugurated Fellow, Center on Global Energy Policy at Columbia University, Co-Director of Energy and Environment Concentration, School of International and Public Affairs, Columbia University. And Professor Dr. George Artman, ICEF Steering Committee, Retired Chair of Energy Systems, Faculty of Process Engineering, Berlin University of Technology, President of the Board KSB Engineer AG in Berlin. And I'd like to ask Professor Sandalo to moderate this session. Professor, please take the floor.
Thank you very much. Good afternoon, everyone. Are you having a good time? Great. What an amazing dialogue. This is just unbelievable. It's amazing. The high quality dialogue at ICEF, it's really so impressive. Thank you to Chair Tanaka, thank you to Mehdi and NATO, to everybody who made this happen. And I'm very excited about this session because we're going to be talking about an extremely important topic, and we have an amazing group of speakers to address the topic. So low carbon hydrogen is a very important part of many net zero scenarios. In order to decarbonize heavy industry, iron and steel, chemicals, in order to decarbonize shipping, for long duration storage, and maybe other applications, low carbon hydrogen is extremely important. But there are some big challenges when it comes to hydrogen. First of all, most hydrogen in the world today, almost all hydrogen in the world today, is made from fossil fuels. And when you make black hydrogen from coal or gray hydrogen from natural gas, that does not help with decarbonization. What helps with decarbonization is green hydrogen from renewables, pink hydrogen from nuclear, or blue hydrogen from carbon capture and storage. It's the rainbow, the hydrogen rainbow, people call it. But we need to get to the pink and to the blue and to the green in order for hydrogen to help with decarbonization. And then, very important, hydrogen is actually an indirect greenhouse gas. And I think too many people who work with hydrogen don't pay enough attention to this. Hydrogen doesn't capture heat. It's not a greenhouse gas. But it does extend the life of methane in the atmosphere. And as a result, it has an indirect global warming impact. And so it is very important as we scale up hydrogen of any kind, whatever color, it's very important that we make sure it doesn't leak, because if it leaks, then we can reduce the climate change benefits of using that hydrogen, which gets us to infrastructure, which is really the focus of what we're talking about in this session. How do we build up the infrastructure to develop hydrogen, to make hydrogen, to move hydrogen where it needs to go? And in particular, how do we use the hundreds of billions, if not trillions of dollars of infrastructure that we currently have for fossil fuel infrastructure like natural gas? Is there a way that we can use that infrastructure for hydrogen? If we could, it could be enormously beneficial. So those are some of the topics we're going to be talking about in this session. With that, let me turn it over to my colleague and friend from the ICEF Steering Committee, George Erdman.
Thank you very much, David. Yeah, in my life, when as scientist, I had been faced 3 times with hydrogen hype. The first was 1980. The task was how to become independent from near Orient, the oil industry from Iran, Iraq, etc. And after some times, this hype was down. Second hype was 2020. The driving force was the car industry, who wanted to diversify its fuel base. 5 years later, this hype was down. Now we are in the third hype or at least I am in the first hype of hydrogen. And except from these reasons, what David has mentioned, one important function of the hydrogen is storage of energy. We have, if we produce electricity, we have no real storage in large quantities. In particular, possibility to store summer electricity for using it for heating in winter and inverse. So this is the reason that we have today a hydrogen in also. And my question, and I hope I will get an answer on this, will this time the hype last?
That's a great framing. Thank you. Thank you, George. So we have 5 great speakers, as I said. We're going to start with Roland Roesch, who is joining us from someplace else. You can tell us where you are, Roland. But thank you for joining us. We really appreciate it. We hope it's not the middle of the night wherever you are. And Roland is Director of Innovation Technology Center at IRENA, at the International Renewable Energy Agency, and a global expert in this topic. Roland, the floor is yours.
Yeah, thank you. Thank you very much, Professor Sanderloh, Professor Erdmann. Yeah, I'm based in Bonn, and I'm the director of the IRENA Innovation and Technology Center. IRENA headquarter is in the United Arab Emirates, and we are a governmental organization with 170 member countries, and we are advising governments, the governments of the world, kind of with a full mandate in regard to the global energy transition and ramping up renewables. And of course, there, the green hydrogen as an energy carrier is an important part of the work we are doing. And if there is a possibility to show my slides. Yes. Just to see where are we with this hydrogen, and let's say what is the hype behind it, what are the drivers, and where is the world going globally with regard to green hydrogen. The next slide, please. We have analyzed the entire value chain of green hydrogen, and actually we were able to start our hydrogen work because the Japanese METI asked us to provide a first study on green hydrogen and the link between renewable energy and green hydrogen, and how green hydrogen can be used in the energy transition under their G20 presidency in 2018. And that was the start where we started the work on hydrogen. And you can see we have looked into the cost and what are the critical carrier of the costs of green hydrogen. We produced a trade triology of about what technologies are needed to trade hydrogen, what certification policies are needed. And we also did a simulation and a modeling of the global hydrogen flows. We did a report on how the green hydrogen can change the global geopolitics. And the latest report we did on behalf of the Italian G7 presidency, we looked into the use of green hydrogen in the so-called I don't want to use this word anymore, the hard-to-abate sectors or the end-use sectors. And there, in reality, let's say, is the key driver. No? If we want to decarbonize certain sectors of the industry, so the chemical sector, it was mentioned, there is already 100 million tons of hydrogen produced from gray hydrogen, from coal and fossil fuels, which is mainly used in the chemical sector, which needs to be replaced. But then also to decarbonize the steel manufacturing, there is no other way to decarbonize the steel manufacturing, only by using green hydrogen to kind of reduce the oxygen in the iron ore. So, and also, last but not least, of course, there are sustainable aviation fuels, but let's say, and also biofuels. But I think the key enablers of decarbonizing the aviation and the shipping sector is will be coming from e-fuels based on green hydrogen. The next slide. So here on this slide, you see different studies that look at what will be needed. So by now, we have a little more than 100 million tons of hydrogen, mainly from gray hydrogen. And then you see, let's say, different studies here. They are more or less aligned, saying, okay, by 2050, so IRENA's scenario, more than 20,000 terawatt hour of electricity demand for green hydrogen production will be needed. So this is almost as much as electricity as we consume globally today from all sources. So the global generation of electricity is something around 20,000 terawatt hours. So that means in 2050, this supply of electricity will be needed to produce the green hydrogen that we need to decarbonize the end-use sector. This, of course, has implications for the investments in the infrastructure, the generation technologies. We need substantially more renewable energy. We need to build up a grid infrastructure, but also an enabling infrastructure with kind of integrating the end-use sector with EV charging, electrolyzers, but also the use and repurposing of natural gas pipelines, the setting up of hydrogen pipelines, and also digitalization and artificial intelligence and big data will play an extremely important role in all this. So we need a smart approach to integrate the electrolyzers in power system synergies with renewable energy. There is also some innovation needed because, let's say, we looked into that at IRENA. So you cannot just integrate the electrolyzers into the existing energy system and then you use the excess electricity to feed the electrolyzers when electricity oversupply is there. So that doesn't work. The reason is you need dedicated supply for the electrolyzers because you cannot ramp up and ramp down all the time the electrolyzers. There is some ideas in place to use module-based electrolyzer systems, but this has still limitations. So more innovation is needed to better integrate the electrolyzers into the energy infrastructure. Next slide. So given the relative scarcity of green hydrogen and its price, we see priority uses for hydrogen in the end-use sectors, and other sectors should be electrified. So you see here there is, let's say, of course, electrification will increase by from 22% currently globally to over 50% by 2050, which would allow us to electrify many parts of the end-use sector. But as I said, some of the sectors you can only go through indirect electrification, so meaning using electricity and water electrolyzers to produce green hydrogen. And there we see the dominant use, especially at the beginning because of the inefficiencies of the value chain to produce renewable power from renewable sources, then to produce through water electrolyzers green hydrogen. and then to produce methanol or ammonia, and then to crack the ammonia again is quite a challenging in terms of efficiency. And that means also given the cost, let's say if you speak about the cost of green hydrogen, it's not yet competitive to fossil fuel-based hydrogen. It depends a little bit. In some places where you have very cheap renewable resources available, competitiveness is already there. And of course, what pays in is that the green electricity generation, specifically from solar PV, but also from onshore wind, offshore wind, has become tremendously cheap in the past 10 years. This helps to produce green hydrogen. The other cost factor is the capex of the electrolyzers, and there we see that the capex in the last 4 years has gone up because of problems in the supply chains, problem in regards to skilled working forces, but also the increase of cost in critical materials. And in reality, we have to bring down the electrolyzer capex from 1,200 US dollar per kilowatt installed to something like 600 US dollar per kilowatt installed, so electrolyzer capacity. So there is still a job to do to ramp up the manufacturing of electrolyzers to bring down the capex to create competitive green hydrogen. Next slide. So this analysis here shows that 1/4 of global hydrogen demand would be traded internationally. So not the 600 million tons that were on this first slide will be fully traded, only a quarter, like 150 billion tons, will be traded internationally. Of the hydrogen that would be international, be traded by 2050 in IRENA's 1.5 degrees scenario, around 55% would travel by pipeline. So the transport would go through repurposed natural gas pipelines or specific hydrogen pipelines. And most of the hydrogen network would be based on existing natural gas pipelines that would be retrofitted to transport pure hydrogen, drastically reducing the transport costs. The remaining 45% of the internationally traded hydrogen, which would be about 67 million tons per year, would be shipped, and predominantly as ammonia, which would mostly be used without being reconverted to hydrogen. Also commodities such as methanol and synthetic fuels will be traded. This is also specifically important for Japan. So I think the hydrogen will come to Japan likely as ammonia, to a certain part also as methanol. But of course, Japan is using a special technology with liquid liquid hydrogen carriers. Next slide. You see here, let's say, there is, of course, the way you transport the green hydrogen depends predominantly on the distance. So with a wider distance, over 10,000 kilometers, you end up with ammonia. But in shorter distances, up to 4,000 till 5,000 kilometers, also the transport over pipelines is important. IRENA is working with ports and harbors and also with the shipping sector, with the International Maritime Organization, but also with the International Chamber of Shipping and the Global Maritime Forum. We are looking into ways and decarbonizing the shipping sector. And let's say the shipping sector is quite efficient, also based on heavy sour fuel oils. But what we have to see is that the shipping sector will play a dominant role in the trading and in the logistics of the green hydrogen, let's say, between the different countries. And there is a big possibility when this sector moves into the logistics in providing and shipping the green hydrogen in hubs and harbors and with ships, that also this sector can be decarbonized. We are just working on a study related to this. The next slide. Next slide, please. In overseas trading, different carriers are included. I mentioned already the ammonia, but also the liquefied organic hydrogen carriers, and the liquid hydrogen could become viable. Ammonia is already produced and stored and traded on large scale, over 120 ports, and this is what I'm saying, play an important role in the logistics of hydrogen, specifically with an ammonia infrastructure. Ammonia can be used as an industrial feedstock and as a maritime fuel next power generation, and the cost for transporting hydrogen via liquefied organic hydrogen carrier are comparatively low. We have done a study there on behalf of the Japanese G7 presidency 2 years ago. So the liquefied hydrogen carrier have some cost competitiveness advantage, but it is not so widely used. So carrying hydrogen through ammonia and methanol is more widely used, and let's say some work needs to be done to implement more the use of liquefied organic hydrogen carriers. Next slide.
And Roland, this is your last slide, I think? Is that?
Yeah, this is my last slide, yes. Just to say, it is extremely important to harmonize the certification and the quality infrastructure. Certain standards are needed to make sure at the end we are able to create a market for green hydrogen. IRENA is working there together with the International Standardization Organization, also with the International Electrotechnical Commission and many other players, to set up the harmonization of quality infrastructure with elements of metrology, testing, and let's say all aspects of certification and standardization that helps to create a green hydrogen market. I think the key challenge is to bring down the cost for green hydrogen, to make sure that more climate finance is used to ramp up the green hydrogen production, and let's say to bring more green hydrogen projects to final investment decision. Only 4% of the projects that are in development have come to FID, and there a lot of work is to be done to create an international green hydrogen sector to decarbonize the end-use sectors and to achieve the 1.5 degrees scenario. I would like to stop here with my presentation. Thank you.
Roland, thank you very much. That was a tremendous background and really sets the floor for the discussion that we're going to have for the rest of the session. And now I'm delighted to introduce Chen, who's a postdoctoral researcher at Carnegie Science, for her presentation.
Thank you for the introduction. Okay. How to play this? Okay, thanks for having me. It's my great pleasure to be here to share my perspectives regarding the low carbon hydrogen. So today I would like to share 3 points. The first is that low-carbon hydrogen can support a net zero emissions transition, especially in those hard-to-abate sectors. And second is low-carbon hydrogen is in its infancy, so massive investment may be needed to reduce the cost in both hydrogen technologies and upstream electricity. The third, I would like to share that global cooperation can help to address the mismatch between the supply and demand, and also to manage the material requirement. So first, I would like to introduce globally, low-carbon hydrogen is expected to play an increasing role in the hard-to-abate sectors. So this figure shows the global demand of hydrogen both from the unabated fossil fuels as well as the low-carbon hydrogen into the future. So currently, the global demand of hydrogen is about 100 million tons globally, and mainly from unabated fossil fuels, from natural gas, from coal. So about half of them will go into the oil refining sector, half will go into the chemical sector. However, with the climate change mitigation progress, into the future, the unabated fossil fuel hydrogen will decrease very fast. So instead, the low-carbon hydrogen will increase very fast into the future. And here, the low-carbon hydrogen will mainly comes from 2 sources. The first is abated fossil fuel. The second one is electrolysis from the wind and solar, etc., renewable energy. So actually, the final demand sector will also be more diversified. Except from the current existing chemical sectors, in the future, the transportation sector, like the heavy-duty road transportation, aviation sector, and the maritime transportation sector, will need hydrogen because hydrogen has very high energy density, as well as it can reach a very high temperature. So the application in the industrial sector, like the iron and steel, and also new chemical sector, will increase as well. So from the supply side, the hydrogen will go from the fossil fuel-based hydrogen to also renewable energy-based hydrogen. While for the demand side, hydrogen will become from only a material to both a material and the energy carrier. So although the low-carbon hydrogen is very important, however, currently the global investment in hydrogen is very small compared to what we needed to achieve the net zero transition. So this figure shows the currently announced and required investment into hydrogen until 2030. So we could observe, in each sector of the hydrogen supply chain, from both production to transmission and distribution to the end-use sector, there is a huge gap in the investment required with what we already commitment. So actually, this is kind of a chicken and egg problem, because if we don't have a low-cost production supply for hydrogen, there is no momentum for the transmission and distribution sector and end-use sector to invest into hydrogen utilization. So without the support of the downstream supply chain, there is also no momentum to put into investment into the production. So actually, the efforts should be put into every single sector of the entire supply chain to make truly progress. So next slide, I would like to show an example of the renewable energy-based hydrogen, like how to move from the current high cost of low-carbon hydrogen into the future, kind of competitive low-cost hydrogen. So based on the calculation, the electrolyzer and energy costs are likely to be the key drivers of the low-carbon hydrogen cost decline. So basically, we need to make progress into the technology, especially like the electrolyzer, to truly make progress on the learning curve. Actually, according to the learning curve, the solar power price decreased about 90% in the past decade, but for the electrolyzer, the cost, we also need investment to make progress into the learning curve. And the second, the green hydrogen price will also be benefited from the lower cost of renewable energy of the wind and solar power. So in this sense, we could pass on the cost competitiveness of the low carbon electricity to the low carbon hydrogen. And the low carbon hydrogen could be further utilized into the downstream sector, like the green steel, to further lower down the cost of the entire supply chain. However, cost is not only challenge. Here, I would also shade the other challenge is the demand and supply mismatch of low-carbon hydrogen. So this map contains a lot of information. So each bar in each country or region represents the total potential of the low-carbon hydrogen production, and the color of each bar represents the cost category of this hydrogen manufacturer. So if it's red or orange, it means that imported hydrogen would be preferred. If it's in green color, it means that it's huge potential to export hydrogen to other regions. And blue color shows the demand center of the future hydrogen demand. So apparently from this figure we could observe like the future demand center, they either have like low potential in production or with a high cost. So definitely globally cooperation would be needed to transfer these high potential, low cost hydrogen from either like South American countries, Middle East countries, Australia to those demand center. And another challenge I want to mention is the key materials utilization in the electrolyzer and fuel cells. So here shows an example of the PEM, the protein exchange membrane electrolyzer. So during the manufacture of this kind of electrolyzer, we will need input from the platinum and also iridium from the supply chain. But currently, all these metals are concentrated and attributed to the supply of South Africa and a few countries. So here are two questions for us ahead of us. The first is that how the fluctuation of the cost of these key metals will influence the cost of electrolyzer, as well as the downstream cost of the hydrogen. The second question is that whether the economic reserve of all these metals will be sufficient enough for the future massive production of the electrolyzer. So, it's not working. Okay, so here summarize my 3 points here. The first is low carbon hydrogen can play a role in the hard-to-abate sector decarbonization. Second is low carbon hydrogen is still in its infancy, so massive investment would be needed to reduce the cost further. The third is global cooperation would be needed in massive ways to address the mismatch between supply and demand, and also to manage the material requirements. So that's all. Thank you very much.
Chen, thank you very much for that really interesting presentation. I think the point you made about minerals and the need for platinum metals, for example, doesn't get a lot of attention. And maybe just could you say another word about that? Do you think that the supplies could be diversified? Do you think that innovation is possible so that different metals would be used?
Definitely. I think like two efforts probably would be needed. The first, like the technology advance. For example, if we have a higher efficiency of the electrolyzer, so this means like proportionally we will need less electrolyzer into the future. So we'll release the pressure of the metals. And I think that additionally, we will also need the market mechanism from the global perspective. For example, we could have like long-term contract to ensure the price fluctuation of all these metals wouldn't be transferred to the downstream utilization.
Well, thank you. Our third speaker is JJU, who's Vice Chairman of SK Group and CEO of SK Americas. Thank you for joining us here at ICEF.
Thank you. Konnichiwa. Good afternoon. And thank you very much for inviting me to this very prestigious event. My name is JJU, Vice Chairman of SK Group. And it seems to be I'm almost the only one from the private enterprise. And it's a bit scary talking with professors, researchers, and experts group. So I will try to convey some the commercial or realistic views. And if I briefly spend time PR purpose for our group, SK Group is second largest conglomerate in Korea, very diversified group, and is open and make an analogy of ExxonMobil, AT&T, and Micron combined group in Korea. And currently I'm CEO of SK On, which is an electric vehicle battery manufacturer. But the reason I'm here is first, Tanaka-san invited me. And the second, I spent 25 years in the energy sector, starting from coal business, and then oil, E&P. First half was in the oil and hydrocarbons, and the second half was we set up a company, SKENS, as a flagship company for energy transition and new energy. So I started LNG, power plant, renewables, hydrogen, and ESS, and also other energy solution businesses. So through almost 27 years, from coal to this new hydrogen, we experienced a lot of setbacks, but moving toward energy transition. And another reason I'm here today is I'm also playing the role of chair of International Committee of Ham Institute for American Energy. This institute was established by the American oil tycoon, billionaire, Mr. Harold Ham, and I'm the business relation is more than 10 years. I'm helping him as a board and also chair of the International Trilateral Energy Security Committee. And I believe US, Japan, Korea has a lot of areas that we can work together so that we can improve in terms of 3 dimensions. For the last 30 years in the field, my experience tells me that the energy sector, whatever area, the economics, affordability of energy economics, and second factor of environmental friendliness, net zero, and third, energy security. These 3 factors, sometimes balance changes, priority changes, but you have to consider these 3 factors all the time to be sustainable. And in that regard, Japan and Korea is, for the time being, will be the importer, while US is exporter. So 3 parties, 3 countries' collaboration will create a lot of synergies. And this Ham Institute, I'm leading this initiative of trilateral energy security issue especially. And today, before start, SK also in hydrogen area already started major project, and soon this year, we finished the factory completion, and from next year, we'll start the world's largest hydrogen liquefaction plant in Korea, which will supply more than 30,000 tons per year. And also, we already established a joint venture with American Plug Power to set up this, to produce hydrogen equipment and the building gigafactory and also R&D center in Korea. So we already started a lot of initiatives in the hydrogen area. And as I mentioned, this energy security point should be also reflected, not just the technical, economics, and other factor, environmental friendliness. So in that regard, hydrogen must be one of the key components also from energy security standpoint. Okay, because time is running out, I'll move into the main point. This old concept, but it was only 2019, only 5 years ago, suddenly getting the attention of hydrogen. Before this, there was no single major report to include hydrogen into the energy mix, long-term energy mix. So it was only 5 years ago that getting the attention. At that time, as I mentioned, this first hype, but already this year and last year, begin to talk about make or break. And I think it's a lot of reasons after COVID, economic situations, but a lot of progress has been blocked and setbacks. Why is it happening? I believe everyone can remember this hydrogen shot, 2021. The Department of Energy in US announced their hydrogen shot 111, which is making 1 kilogram of hydrogen at $1 in 1 decade. I think that was June, and July I met with the director of this DOE. He was very confident that he can achieve this goal, and he explained the detailed plans of how they can reduce the cost of each component of the value chain, manufacturing, especially electrolysis. But after 4 years later now, if you see the reality, I'm so glad that Chen just explained. On the right-hand side chart shows that what might be the likely cost of producing 1 kilogram of green hydrogen. It varies a lot. The chart looks very busy, but I'm going to talk about the realities. US government of this program started a $3 subsidy program for green hydrogen. And then hydrogen industry was very enthusiastic about that program, but in reality, a couple of months ago, they announced the conditions to be regarded as a green hydrogen, 3 conditions, so-called 3 pillars. One is time matching, and second, regionality, and also additionality. After this, I think that getting subsidy of $3 was almost impossible. So The initial target was $6, but in reality, without getting this subsidy, and also in US, one of our partnership projects, the EPC cost has went up so much. And also the major component, the power, renewables cost has also increased. As just the Chen just explained, to lower the cost, renewable cost should go down $1.3 or at least $1.5, but renewable cost is already very competitive, but further lowering more than $1 seems to be very difficult because their speed of lowering cost is already saturated. So arriving $1, but to me, this chart in reality, even $2.6 they targeted might be very unlikely. So 2030, so in reality, all those projects we did in US, even though the goal is very ambitious, very difficult to target and challenging, it's not just the technology limitation of hydrogen itself. To people like us, the whole value chain cost should be competitive, otherwise we cannot compete. And the EPC cost, the renewable cost, and the electricity and all major equipment cost should be lowered simultaneously, otherwise very difficult to achieve. So what I'm saying is production, storage, transportation, consumption, all areas, we need simultaneous progress, but where to start might be from market viewpoint, it's always the demand creation. Without long-term commitment of the demand, people will never start manufacturing it. So government role and the policy goal should be creating long-term demand commitment from government or the institutions. And I'll skip, because he's pushing the time limit. I will talk about this, but we have to get the lesson from this chart. Prepare this, China's electric vehicle. Because I'm also CEO of SK On, which is electric vehicle battery manufacturer, their cost competitiveness and technology, everything is so amazing. And now, Chinese electric vehicle, last year, 14 million cars of electric vehicle was sold. Out of that, 8 million cars of unit was manufactured and sold by Chinese. And also, you talk about the raw material, but the EV batteries, 50 to 70% of raw material is coming from China. And at the moment, I think Chinese electric vehicles very, very competitive in terms of cost, in terms of quality. Then I think we have to get some lessons. It took more than 20 years of very substantial and consistent support program throughout whole value chain. This created the demand and supported the cost competitiveness of each component of the value chain. So we talk about piece by piece of the hydrogen value chain. I think we have to think about overall value chains. As a result of that, in 7 years, Chinese electric vehicle market has increased 70 times bigger. He's showing me so I will skip everything, but if you see what I'm saying is creating demand, Japan and Korea combine the market, but even the definition of green hydrogen itself is different. This chart shows that each country applying different concept of definition of green hydrogen. The reason to have the common definition is creating common market, bigger market, so that commercial sectors can move in more visions are more active. Chen also mentioned everyone say huge investment is needed, but how we can draw or invite those investments starts from clear definitions and regulatory frameworks so that commercial players can see the market, bigger market, so that they can have the bigger investment potentials. Yeah. This chart shows that Japan and Korea combined market will be the second largest hydrogen importer and market in the world if we work together. And also US, because of IRA, their cost competitiveness can be as good as Middle East. And sometimes some regions still, at the moment, they can produce at $2 or $3, below $3. But I'm talking about overall general level of production. So US as an exporter and Japan and Korea importer, if we work together, I think we can create a lot of progress in this hydrogen frontier. I will skip this. If I briefly introduce, Korea has been advanced in developing this regulatory framework. And already 3 years ago, we started this. And then now program is KEPCO. Korea KEPCO is buying hydrogen additions in the power generations by subsidizing the gap, cost gap between the traditional one and this expensive hydrogen added power generations. This bidding already started, so I think sooner or later, latest from next year, this program will be really executed. So in a sense, Korean government is very committed about this further progress. It's always the money that how you're going to allocate to the subsidy, the funding, renewables, hydrogen. There are a lot of competing items to get more subsidies. So that's why I'm saying like Chinese government developed electric vehicle industry, substantial, consistent support program so that we can have the predictability. That might be the incentive for commercial players joining into this region. Okay? So, because I'm talking about Japan, Korea, US collaboration, MURAKI-san is my senpai and knows a lot about this area, but Japan, Korea, for example, will import, as already many people mentioned, ammonia might be the most effective and efficient carrier to import this hydrogen. But Korea is already importing more than 1 million tons of ammonia, whereas Japan is only importing less than 300,000 tons per year. And in the western, especially western part of Japanese island, it's shallow area, shallow sea, so Korea is closer to, for example, Ulsan port has a large tank terminals for ammonia, so bulk breaking from Ulsan might be lowering 20% of transportation cost. I know that MURAKI-san explained further details about this area, so there are many areas that we can collaborate together in technology or regulatory framework rule setting. And this electrolysis area, whether it's SOEC or all these areas, there are many areas we can combine.
Excuse me, we have another 2 speakers and just
I'll finish here.
10 minutes time. So
Okay.
thank you
very
for
much.
your speech.
I'll finish here.
Thank you. Well, the place you ended is the perfect place then to transition to our next speaker, Shigeru MURAKI, who is president of the Clean Fuel Ammonia Association here in Japan.
Thank you, David, and thank you, Tanaka-san, for inviting me to this very important event. I left gas company, and I now moved to the Clean Fuel Ammonia Association. I moved from, I left smells carbon and moved to the smell of ammonia now. And this is an organization, it's a very young organization established April 2019. We are supported by 244 members from 17 countries. We are trying to provide a collaboration platform in industries between government and industries and international. Why ammonia? Ammonia has established technologies and systems in production, storage, and transportation through the 100 years of the history, and efficient in the transportation and storage of hydrogen. Therefore, the ammonia is the most pragmatic hydrogen derivative. And also, ammonia can be combusted in energy systems, various energy systems. So the efficient and effective zero-emission fuel through the direct combustions in the power generation, coal power, gas turbines, industrial furnaces, marine diesel engines, and chemical process, refinery, and steel production eventually. And World Bank, we had a meeting with them recently, and they stated 46% of all plant electrolyzers capacity is expected to produce hydrogen for ammonia production. So they mentioned that if we need to promote hydrogen, we need to promote ammonia. Technologies of direct combustions, ammonia substitution in coal-fired boilers. The JERA conducted large-scale demonstration in their 1 gigawatt coal power, 20% mixture of the ammonia, and they confirmed the emission control, no increase of NOx emissions, no N2O emissions, non-unbound ammonia. So they are now moving to the commercial phase, and they will start the commercial use of ammonia in around 2027. And the main target of the power generation is gas turbines. 2 companies are working on that, and 2 megawatt to 60 megawatt gas turbines, they are developing very well, and single fuel gas turbines will be developed by around 2025. 300 to 400 large size combined cycle gas turbines will take a little more time, and through the 2030s. In the 2030s, I think it's the lineup of the gas turbines will be ready into the market. And industrial furnaces, Taiyo Nippon Sanso is working with Asahi Glass and development of the ammonia single fuel burners, and they will finish the development of the burners in 2025. And very important development is marine diesel engines. Small 4-stroke engines already finished the development, and it is installed in the tugboat by NYK in August this year. And they are conducting the safety test of the ammonia utilization in engine room. And large diesel engine will be finished by 2026, and the first ammonia-fueled ammonia carrier is planned to be launched in November 2026. Japanese government is preparing about 3 trillion Japanese yen for 15 years it's a 22 billion US dollars to subsidize the cost difference between ammonia or hydrogen and the existing fuels for the first movers. Starting by 2030. And ammonia has a lot of supply potential project, and they are working to propose to this CFD program. And in the market side, we are planning the hub and spoke system. Now, 6 areas and 8 terminals are proposing the hub terminals. And of course, as JJ mentioned, and it's not the chart doesn't show that the Korean part, but I think the Korea and Japan can share the hub terminals to deliver the ammonia to the various areas of the demand. And the demand, forecasted demand in Japan in 2030 is 3 million tons, mainly from the coal power plant. And we are working on the collaboration between Japan and Korea for the supply chain development. King conditions a long-term contract with the price formula, particularly in the blue ammonia from United States, and we are planning to use the Henry Hub price. And low carbon intensity is very important. The threshold of the carbon intensity for the blue ammonia in Japan at the beginning is a 70% reduction of carbon dioxide from the existing gray ammonia from natural gas. And of course, on destination flexibility is very important to share the supply chain between Japan and Korea. That ends my presentation. Thank you very much.
Thank you, Muraki-san. And our last speaker is Eniya Dewi, who is the Director General at the Ministry of Energy and Mineral Resources of Indonesia. Thank you for joining us.
Thank you so much. Did I just have 1 minute, maybe? So
I think you take as long as you want. We want to hear from you. Yes.
So hopefully you will not go so overwhelmed with the hydrogen and ammonia, because I will give you more. So regarding to the Indonesia situation now about the energy transition, we have abundance of resources. So everybody about talking about the producing the hydrogen. So we have a very big potential of hydrogen production countries. And if we look at the resources, we have more than 3.6 terawatt. So this is a big potential. And the biggest is solar, wind, and then the last thing is geothermal. And of course, if we put on the map the hydrogen production potential that we can get from each island, because it's more than 14,000 islands in Indonesia, and we have 5 big islands. This would be the big potential that we can produce the hydrogen from here. And the Kalimantan Island would be the biggest one from hydro. And we can addressing more on the another island is from the solar. The solar is the yellow one, and you can get a blue one from hydro. And the interesting thing is that we are now the visit of the electricity. So there is no more oversupply in Java. This is the main island of Indonesia. And you know, Indonesia growing to make the smelters. And then we are now need a green electricity to supply the smelter. More of the smelter industry located at Sulawesi with the K island. So this potential have abundance of solar and also geothermal at that location. And with the eastern part of the Indonesia, we can get more hydro and solar as well. So regarding to this position, Indonesia also want to be a part of the global hydrogen hub in the supply chain, especially for Indo-Pacific region. And this is the first time also that we are mixing the hydrogen and ammonia in our national energy planning. And the first one also, we will use nuclear power plant in the next 2032. So this is really a good movement of Indonesia as well. In the bottom of the map, you can see the gray one. This is the coal. The coal users would be a peak on the 2030, but it slightly reduced the use of the coal after 2035. So we replace it with the renewable one. And the hydrogen would be 25 gigawatt, and then ammonia would be 41 gigawatt if we're talking about the electricity uses. And of course, now we have a national strategy of hydrogen. In the first step, we will go in the export market, then we're creating the domestic market. And the use, of course, in the industrial, transportation, and electricity, and also as a commodity. So we have a demand of the hydrogen right now. The biggest the user of the hydrogen is in the fertilizer industry. Now we are also exported the ammonia to another countries. So regarding to our analysis, we have a potential to make an export of the hydrogen and ammonia. And then we will have a detailed hydrogen and ammonia roadmap, because we will definitely go with the net zero emission in 2060, and there is many commitment that we will reduce the coal uses in our electricity and industry. And we have an action plan of the hydrogen. Of course, we start with the initial steps, and then we'll go to the sustainable hydrogen future in the 2060. And of course, in between, we will make an infrastructure, integration, and need many collaboration with the other countries to making the more mature hydrogen ecosystem. And of course, now we have 22 locations that we optimize the electrolyzer uses in the power plant. We're creating the green hydrogen over there. And the first one is come from geothermal. It's located at Java Island. So we have green hydrogen production from geothermal. And then now we have also from this year, in early of this year, we have the first hydrogen refilling station. And then in next year, we will have the hydrogen road test in Jakarta. So maybe you can visit Jakarta. This is in the main road of the Jakarta. And we start also the hydrogen center. Many people now enthusiasm with the hydrogen in Indonesia as well. And we're creating many training facility in this location. And regarding to our collaboration in industrial sector, there is many movement of the hydrogen pilot project that using co-firing hydrogen, co-firing ammonia in the power sector. We collaborate with Mitsubishi, IHI, and another 4 pilot projects that now is going to, a few of them is funded by NATO and so on. And of course, we are also thinking about the bunker of ammonia we can produce. And we are now have a planning in the north part of the Sumatra island. There is the big user of the hydrogen in the fertilizer industry. So we want to make green ammonia at that location. In this part, in the in the east part of Java Island, we have also petrochemical industry in Gresik. And we have now progressing the hydrogen produced that from the biogas. Because we have many abundant of the waste of the palm industry. It's much more on the Sumatra Island. And then there is many study that we had already a lot of biogas installation. And the last thing that I want to share to you that we are also creating the standard, including the standard of the ammonia and also the standard of hydrogen. And we have preparation of the many regulation that we will have in the Indonesia. And there is many enthusiasm for industry to make the regulation, to make a support for us. And thanks for the collaboration. And the last thing, Indonesia have a position, we make a statement of the hydrogen and global that we joining the APEC. And all of the APEC country now have guidance to develop and implement it clean and low carbon hydrogen policy in the Asia Pacific. So this is a good movement, I think, to creating ecosystem, and then the Indonesia also want to be a part of the global supply chain. Thank you so much. That what we can share for you today. Thank you.
Such great presentations. I wish we had another half hour to have a discussion, but we don't. We have about -1 minute left in this session. But we've discussed technology, we've discussed markets, we've discussed policies. We didn't come back to the issue I started mentioning, which is that hydrogen is an indirect greenhouse gas. And I think it's worth keeping that in mind, that it's the smallest molecule. If it leaks, it does create problems. So as we scale up infrastructure, we really need to pay attention to that. But I'm really grateful for the organizers of this great session. And please join me in giving our speakers a big round of applause.